Okay, so we have seen that linear regression, assuming that our outputs are scalars, so the yi, is fitting a curve or a line to the data that we have. So we have data points, these pairs xi, yi, where xi is some input and yi is some output or target, and we have n of them. And we want to fit a curve or a line to this data. So the simplest case would be just a scalar function of a scalar input. So we'd have these y's depend on some scalar input x, and we might have something like this, right? So what do we want to do? We want to fit, maybe move that over there. We want to fit some sort of curve or line through this data, right? That's our goal in regression. So that once we've done that, we can make a prediction. So these correspond to our data points, the values of x and corresponding values of y. And once we have this curve, we can make a prediction at any point x. So this is the way we've been viewing linear regression. What we're now going to do is see linear regression as a projection of our data. So let's focus on the outputs here. Let's define the vector of our outputs, y1 up to yn. We have n of them. And call this vector y. And where does it live? It lives in Rn, Euclidean space Rn. We are now going to think of linear regression as projecting this vector onto a subspace of Rn. Right? We're going to project this onto some closed subspace of Rn, call it S. So this lies in Rn, and we're going to project it onto some subspace of Rn, so only a portion of Rn. So Rn is a huge space, right? And what we're going to do is project this y, right, our vector of targets, onto just some portion of Rn, a subspace we can call S. And we want to characterize this subspace. We want to see exactly what this subspace is. So let's remind ourselves of what we do in linear regression from the point of view of ordinary least squares. So this is a particular type of linear regression. And I will explain as we go through what particular assumptions we make to get from linear regression to this particular version of linear regression. We want to approximate our targets or outputs yi by some function. So we want to be able to predict y for a given x, and we introduce some sort of function in order to do that. It's a function of x, so it maps from our input space. So we're assuming that our x's or xi's, a general x, let's say, lives in Rd, it has d components. And this function has to map from x, the space in which these x's live, to the real line. So it's a real valued function. And this is the particular form that we assume. It's a linear combination of some basis functions, these psi j. So these are specified, we specify these functions of x. And we have a linear combination, this sum. So each one is multiplied by some coefficient or parameter, theta j's. And we can write this compactly like this sum. We can write it compactly by defining the vector of these theta j's. So we can define theta as the vector of these theta j's, theta 1 down to theta p. And similarly, we define a vector of these psi j's as psi equals psi 1 down to psi p, right? And then we take the dot product of this with this and we reproduce this sum. So this is just a compact way of writing it. So this is our model in ordinary least squares. And we will want to find the values of these parameters, or equivalently this vector here. and we can call these undetermined. We don't know their values. We specify these, and we want to find therefore these. These are the things that we don't know. But the basis functions themselves we specify. So if you remember, the simplest example is that we can specify these basis functions as monomials. So in 1D, if our x's are just scalars, we could specify psi1 function of x, now just considering the scalar, as just the constant function 1. Psi2 of x is the constant, not the constant, the function x. Psi3 of x is x squared, and so on. We can get the pth one here. Psi p of x would be x to the p minus 1, right? And so what do we have? Our model would be a polynomial. F theta of x would be theta 1 plus theta 2 of x plus dot 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 up to theta p of x to the p minus 1, right? So this would be our model. So in this case, as I say, we're using particular basis functions. Psi1 is 1, that's times 1. Psi2 is x, psi3 is x squared, x cubed, and so on until we get to this one. So that's what you might call classical way using monomials. Okay. Now, in ordinary least squares, you want to find the best theta j's, or the best vector theta, and we have to define what we mean by best. And in ordinary least squares, as the name suggests, we define best as the lowest total square error in our predictions of the y's using this function here. Right? So we want to minimize the square error in these predictions. So for each xi, we're going to have a prediction f theta of xi, where we just put xi into this sum, or in this dot product here. And we compare this to the data point that we have, yi. We square that, and we sum over all of our data points. And this is our total square error. And this we want to minimize. We want to find the theta that minimizes this total square error. That's what we do in ordinary least squares. Now, we can equivalently write this model. So our model for each x, we have this model that y is approximately f theta of x, right? Which is that sum, or we can write it as theta transpose psi of x. So this is for general. So let me put I here, so we don't confuse this with the vector of targets. So for each I, this is our model, that yi is approximately f theta at xi, which is defined as this thing here, this linear combination of basis functions. Now we can do this for each xi, and each yi, corresponding yi. So we would have y, our vector of targets. So this is y1 down to yn, is approximately, so this is what this is approximately, we're going to have theta transpose psi of x1 down to theta transpose psi of x n. And we can write this vector as a matrix phi times theta. And what is that matrix? It's this matrix here. So you can see we will reproduce, for example, this as when we do this matrix multiplication, we're going to take the dot product of this with this, which is exactly what we've got here. And the second row will be the dot product of the second row with this, down to the dot product of this row with this. And what is this? This is precisely this thing here, psi at xn. And this is precisely this thing here. And this matrix here we call the design matrix. So our model, equivalently, if we write it for the whole data vector, is y is approximately this design matrix times theta. So we can call this approximation y hat. And this design matrix is an n by p matrix because we've got n data points and p basis vectors. So this is our model for the whole data vector. And then we can express our ordinary least squares problem as this minimization. We want to minimize the total square error, which is this thing here. So explicitly it's this, and we can write it as the dot product of this vector y minus phi theta with itself, or which is equal to the 2 norm of this vector. So this thing here is y minus phi theta dot product with itself, y minus phi theta, which is exactly the 2 norm. Now we put a half in front of it, so this half here and this half here, because when we solve this, what we do is we take the gradient or the derivative in multiple variables, and that will cancel this half. We'll get a 2, which will cancel the half. So this half we put in by convention. It's just to make the algebra look a bit cleaner. We don't have to, because the total square error is this, so we've got half the total square error. But minimizing the square error is exactly the same thing as minimizing half the square error. We're minimizing over theta, the value of theta that gives us the minimum square error, which is exactly the same as the value of theta that gives us the minimum of half the total square error. So this is our problem. We want to find argmin over theta of half the total square error, meaning the value of theta, so this argmin over theta means the value of theta that minimizes this quantity, which is a function of theta. And we call this value of theta, theta hat. So this is our ordinary least squares problem. Now, we're working here in a Hilbert space. So Rn is an inner product space. We can define an inner product on Rn. This is a general notation for an inner product as the standard inner product. The standard inner product is just the dot product, what we call the dot product. So this is just the dot product of two vectors in Rn. So for any u and v in Rn, the standard inner product or dot product is this quantity here, which we can also write if we want like this, u dot v. Right? But we can think of it as a matrix operation. So Rn is an inner product space, and all finite dimensional inner product spaces are complete. So it's a Hilbert space with this particular, we're assuming this particular, we can use another inner product, but we're going to use this particular one, standard. Now let's define a vector of residuals. R of theta, we're going to give it the symbol R of theta, so R is our residual vector, as the vector y minus the approximation of our vector y, phi times theta. So what is this? Well, let's think of what this is. It's a vector, right? So it's going to be the first component of y, y1, minus the first component of this, which is going to be psi at x1. Let me do that again. Let me make this a bit bigger. So we're going to have y1 minus theta transpose phi, a vector of basis functions at x1. So it's our observed value, the value in our data set, minus our prediction of this. And we can call this R1. It's the residual. It's the discrepancy between our prediction and the true value. And the second component of this vector will be y2 minus theta transpose psi at x2, and so on down to yn minus its prediction theta transpose at xn, right? Using our model. So this is our linear model, linear regression model. So this vector of residuals is literally just the discrepancies between predictions and our observations. Then we can write ordinary least squares as this problem here. Find the value of theta that minimizes a half of the norm of the residual squared. Right? Which let me remind you, our original problem was to minimize the total square error, or half the total square error, which is the norm, the square norm of this thing here. And all I've done here is I've just given this a name, r theta, the vector of residuals. So I've just rewritten the problem like this by replacing this with r theta. Right? That's all I've done here. So what is our condition to find a solution to minimize the total square error or half the total square error? Well, it's the first order optimality condition. So if we have a function of one variable, what happens is we need to solve this equation here. So if you have a function of one variable, let me call it f of theta. So theta is just a scalar. We need to solve the f by d theta equals 0. And that's where a minimum or a maximum occurs. And this we call first order optimality. First order meaning we only use first order derivative information. Now the equivalent of that, if f is a function of a vector theta, the equivalent of this would be gradient of f with respect to theta is equal to the 0 vector, because this is a vector. Right? So first order optimality for a function of one variable scalar is this, and for multiple variables is this. And this leads to what we call the normal equations in ordinary least squares. Because what is the gradient of this thing here? It's the gradient of y minus phi theta, dot product of that with itself, y minus phi theta, right? And the gradient of this, we're going to get a 2, which will cancel the half. We're going to be left with this times phi transpose, which is what we have here. And what is this? This is our vector of residuals, r theta. So we end up with, so these are what we call the normal equations. This equals the 0 vector. And we can write this as, using our definition of the residual vector, as this. Phi transpose r equals 0. Now what is this? What does this look like? Well, let's have a look. Let's try to remind ourselves of what phi is, our design matrix. So our design matrix has rows, which are the rows of phi will be psi at x j. So the jth row will be the vector of basis functions evaluated at xj. But what we're interested in here is not the rows, but the columns of our design matrix phi. So let me call these columns phi 1 to phi p. There are p of them because so this is phi, our design matrix. It's equal to this. I'm going to call the columns of our matrix phi. I'm phi 1 to phi p. So these are the column vectors. We can call them column vectors. Now, what size are these? Well, phi is an n by p matrix, so there are going to be p of these columns, and each of them lives in Rn, right? Because we have n components going this way. Okay. Now, when we transpose this matrix phi, so the transpose of this will switch from these being columns to being rows. So phi transpose will look like this. The first row will be this column, phi 1. And the last row will be this column, phi p. Right? And now we're going to have a matrix which is n this way and p going this way. Right? Okay. And this is multiplying our residual vector r. Right? So what is this matrix multiplication? That's what we have here. Well, we're going to take the dot product of this with r. That will be the first component. So this is going to end up being phi 1 transpose r, and then phi 2 transpose r down to phi p transpose r. That's what the components of this will look like. And each of these has to be equal to 0 because this is the 0 vector. Right? So each of these has to be 0. So we get each of these dot products is 0. The dot product of the residual vector with each column of our design matrix is equal to the number 0. Right? So dot product, the standard inner product on Rn will give us a number. So the residual vector is orthogonal to every column. This is how we define orthogonality. The inner product is 0. In this case, we're using the dot product as the inner product. Geometrically, in 2D and 3D, this means at right angles. And it has a similar generalized meaning of being at right angles in higher dimensions. But of course, we can't visualize it. It's not a physical angle anymore, but it's nevertheless a generalized concept of an angle. Now, the columns of our design matrix, phi, span what we call its column space. That is the definition of the column space of a matrix. It's all linear combinations of column vectors, or the image space of our design matrix phi. So the image space is defined as the span or linear span, to be pedantic about it, the linear span of the column vectors. The image space or column space of a matrix phi is the span of its column vectors. And what is the span of its column vectors? It's the set of all linear combinations of the column vectors. It's all vectors of this form. And each of these is in Rn, right? So any linear combination will lie in Rn. So what is a linear combination? It's just a constant alpha 1 times the first one, phi 1, plus another constant alpha 2 times phi 2, etc. So it looks like this. It's alpha 1, phi 1 plus dot dot alpha p, phi p. That's a linear combination of these vectors phi 1 to phi p. That's how we define linear combination, where these are just some numbers, some coefficients, and they can take any value. Right. So here I should, to be strictly speak, I should put here for any alpha I or in R, any numbers alpha I. So all vectors of this form for any numbers alpha I are precisely what we call the span of these vectors. It's the set of all linear combinations. And this is the image space of phi. Why is that? Because any vector phi times theta. So if we take a vector theta and we multiply that vector by phi, what does that vector look like? It will be equal to the first component of this, theta 1, times the first column of this, phi 1, plus theta 2, phi 2, up to theta p, phi p. It's a linear combination of the column vectors. So every multiplication of a vector by this matrix phi ends up as a linear combination of these column vectors, which is precisely what I'm defining here, this linear span, right? And we call this the column space, or equivalently the image of phi, meaning the image of phi is all vectors that are produced by matrix multiplication of this form for any theta. So the set of all of these vectors we call the image space of this transformation or representation of a linear transformation in coordinate form. Because phi takes a vector theta p in Rp and maps it to a vector in Rn, right? And that vector is this a linear combination that looks like this. All of the vectors that it maps to will look like this. So the set of all vectors in Rn given by these linear combinations for any vector in Rp, for any theta, is what we call the image space or column space of phi. Now, R is orthogonal to every column. So R must be in the orthogonal complement of this image space. And we write this orthogonal complement as the image space with this perpendicular sign. So R is in the orthogonal complement of the image space. What is that? It's all vectors V in Rn such that the dot product of V with a vector U in the image space is 0 for all vectors in the image space. So the orthogonal complement of the image space is the set of all vectors V that are orthogonal to every vector in the image space. So why then is R in this orthogonal complement of the image space? Well, let's think about it. What do we know? We know that R is orthogonal to every column vector. So it's orthogonal to all of these here. So let's take a general vector in the column space. What does it look like? A general vector in the column space is of this form. The sum from I equals 1 to P. It's a linear combination of these column vectors, phi I, right? It looks like this, right? So we can call this U. Any vector in this image space, in the image space, is a linear combination like this. It looks like this, right? Now, let's take the dot product of R with this general vector in the image space. So we're going to do R transpose U, which is R transpose this thing here, R transpose this sum. So it's R transpose this whole sum. We could take this inside and put this here. So it's the sum of some numbers times R transpose phi I. But R is orthogonal to every single one of these from I equals 1 to P. So this is equal to 0 for all I. And so the whole thing is 0. So indeed, because R is orthogonal to every column vector, every phi I, it's orthogonal to any vector in the image space in this linear span, and therefore it lies in the orthogonal complement of the image space. So R lies in the orthogonal complement of the image space, and our solution phi theta hat obviously lies in the image space, right? Because the image space is defined as all vectors that we get by multiplying a vector by phi. So what are we doing here? We're multiplying theta hat by phi, and that gives us a vector in Rn, which has to lie in the image space of our linear transformation. Phi, our matrix, as a linear transformation. So our approximation lies in the image space, whereas this residual, the difference between the true data vector and our approximation, lies in the orthogonal complement of the image space. So what have we done here? We've performed an orthogonal decomposition of our vector y. We have y is equal to the approximation of y plus the residual, we can think of as basically the error in this approximation, a sort of error, although it's a signed error, so it's not a very useful one without doing something more, at least taking the absolute values, where this approximation lies in the image space and the residual or the error lies in the orthogonal complement of the image space. And any decomposition like this, we call an orthogonal decomposition of a vector, which is covered in the linear algebra videos in great detail, all of this. So let's apply the projection theorem, which is in the linear algebra videos. I proved this theorem in there. So what is the projection theorem? Well, let's take a general Hilbert space, let me call it H, and with that Hilbert space, I'm going to associate some inner products. So we write the inner product space as the pairing of the space, the raw space, with the particular inner product that we're using, because we can define different inner products, and we're defining this particular inner product. So the Hilbert space, the inner product space we're considering is the set H, or vector space H, with this particular inner product. It's this pairing, which you write like this. So this means nothing more than we're pairing this together with this particular inner product. Now, we're assuming that H is a Hilbert space. So this is a Hilbert space. It's complete with respect to this inner product. Now let V be a subspace of H, a closed subspace. Then for every vector y in our Hilbert space, there is some vector in V, and that vector is unique. Let's call it little v, which is termed the orthogonal projection of the vector y in H onto the subspace V. And we write it like this: V is proj Vy, the orthogonal projection of the vector y onto the subspace V. And that lies in V. The projection always lies in V. By definition, it lies in V. Furthermore, the difference between the vector y and this orthogonal projection lies in the orthogonal complement of V. So we have decomposed any general vector y in our Hilbert space into two parts. One part which lies in V, which we call the orthogonal projection of our vector y onto the subspace V, and the remainder y minus this, which lies necessarily in the orthogonal complement of our space V. So we've got y equals V plus, let me call this R, where V lies in V and this lies in the orthogonal complement of V. And I can take any vector in H, y, and I can write it like this, as a term in V plus a term in the orthogonal complement of V. And we call this an orthogonal decomposition. An orthogonal decomposition of Y, and also an orthogonal decomposition of the space H. Technically, it's an orthogonal decomposition of the space H. And we have one other property, which is the key part of the projection theorem, that this V that we have, this projection, is the best approximation of Y in some sense. And what is that sense? If we take the norm of this difference, y minus v, the error or residual, in our approximation of y by the vector v in the subspace v, then this norm is the minimum of all norms y minus u, where u is in v. So it's the vector in v that is closest to y, right? So let me try to illustrate this. So this is our Hilbert space H, and this is a small portion of that. Let's call it V. It's a subspace of that. Now, Y lies here, let's say. Let's say it doesn't lie in here, otherwise it's trivial. Let's say it lies here, it doesn't lie in V. Now, we want to approximate this as a vector just in here, right? So that approximation of our Y, so this is our subspace V, let's call it V. And this is the orthogonal projection of Y onto the subspace V. Now, the difference between this and this, Y minus V, we can call this a sort of error or a residual, R. And that residual will lie in the orthogonal complement of V. Now, we want to find the best approximation of Y using some vector in here. And this orthogonal projection is that best approximation in this sense, that the distance between this and this, the norm of y minus v, is minimized over all vectors in here. Right? So if I want to be a bit more intuitive, it would be here. So it's the vector that's closest to y but lies in v. Right? And the closeness is measured using the norm that's induced by our inner product. So if we change the inner product, we will change this norm, which is the way of measuring the size of vector. And this is our induced metric from this norm, meaning the way we measure the distance between two vectors. We measure it as the norm of y minus v, one vector minus the other vector, the two vectors that we want to measure the distance between. So this is a measure of distance between y and v. And this all comes from which inner product we choose. If we change this inner product, we'll get a different measure of distance. So this projection theorem, right, is proved in the linear algebra videos in full. We are now going to apply this to our OLS problem. We won't have to do much work because we've pretty much shown everything. So, as I said, V for the general case is the best approximation of Y using a vector in V. And that best is the measure, the shortest distance, where distance is measured using the induced norm, the induced metric, and the norm that we use to get the induced metric is given by the inner product that we've used. So let's apply this to our problem. Our image space is a closed subspace of Rn. So in our case, our Hilbert space is Rn, and V, the closed subspace of H, is the image space of our design matrix. Now, we have just seen that we have this approximation of Y lying in the image space, right? And the difference between this and Y, which is what we're calling our residual vector, lies in the orthogonal complement. Now, these are unique. This decomposition is unique. What we have done here is we've decomposed y into uh, phi theta hat plus r, where this lies in the image space of phi, and this lies in the orthogonal complement of the image space of phi, right? And if we call this V, this is the orthogonal complement of V. V is a closed subspace of Rn. Therefore, we can apply the projection theorem. We have a unique decomposition of Y using this. This is a unique decomposition of our vector of targets Y, where this lies in the image space and this lies in the orthogonal complement of the image space. So this must be, using our projection theorem, the projection of the vector Y onto the image space. It must be, because this is a unique decomposition. And the second part of the projection theorem therefore tells us that this is the projection of Y onto the image space. And it satisfies the following. The distance between this approximation and Y is the smallest over all vectors V, this distance with any general vector V lying in the image space. Now, all vectors V in the image space have this form because the image space is defined as phi acting on some vector, right? So there must be, so for any V in the image space, there must be some theta such that V equals phi times theta. So equivalently, we can write this problem as the minimum over theta of Y minus phi theta. So the projection theorem tells us that this, with our OLS solution, is the minimum over theta of Y minus phi theta, which is exactly ordinary least squares. So this is telling us that ordinary least squares is equivalently the best approximation of Y in the image space of our design matrix. And that image space is a closed subspace of Rn. We restrict our attention to only this subspace. We want to find an approximation of our target vector using a vector in the image space of phi. We only look inside there. We don't consider any other element of Rn, only those vectors that lie in the image space of this. And ordinary least squares finds the best approximation of Y by a vector in this image space. And that best is defined by this 2 norm. The reason we get the 2 norm is because we use the standard inner product. And the norm induced by the standard inner product is precisely the standard 2 norm, Euclidean norm. Right? Okay. Or another way we could say this is the error in the approximation of Y by an element in the image space is minimized in a square sense, right? Which is precisely a statement of ordinary least squares. Now, the ordinary least squares solution is given by this. So we've derived this already. And so we can write the solution as some matrix P times our target of vector of targets P, where this matrix P is defined as follows. And this simply follows from the fact that phi is given by this quantity here, and so phi times theta is phi times this quantity, and multiplied by y. So the Moore-Penrose pseudo-inverse is phi transpose phi minus 1 phi transpose, and that's multiplied by y, and that's what gives us our theta hat. And so we're doing theta times phi times this, and so we leave off the y, and you're going to get phi times this whole thing here, which we'll call p, and that's multiplying y, and that's our approximation, p times y, where this matrix P is a projection matrix. It projects y onto the image space or column space of phi, and it satisfies the properties of a projection matrix, which are first, that it's idempotent. So when we apply P to itself, we don't change P. It just goes back to being P, and it's symmetric. Transpose of P is equal to P itself. So these are pretty easy to show. In fact, very easy to show. So for example, this one here, that's the easier one. So the transpose of this matrix here would be, so we want to do the transpose of this whole thing. Well, it's going to be, this goes first, so it's going to be the transpose of the transpose of phi, which is just phi, times then the transpose of this, phi transpose phi inverse transpose. Now, this is a symmetric matrix, so its inverse is also symmetric. So the transpose of this inverse is just the inverse. And then we're going to get the transpose of this, phi transpose, which is exactly P. Right? And you can show this as well. Just multiply this by itself and you'll see that it turns out to be equal to P. It's a good exercise for you, actually, a bit of matrix manipulation. And that's it. So this is the viewpoint of OLS, ordinary least squares, as a projection of our target of vectors y onto a subspace, and that subspace is the image space of our design matrix, or equivalently the column space of this design matrix.